Over the next 30 to 40 minutes, the Radon team will discuss the technology that powers MICAP-OES 1000. We'll provide a brief demonstration of hardware setup, method development, and data review. Please enter all your questions in the chat, and we will answer them in the order in which they are received at the end of our presentations. So let's sit back, relax, and enjoy MICAP-OES 1000. Before we discuss MICAP-OES 1000, let's first give a brief overview of Radom Corporation. As I mentioned, Radom Corporation is located in Milwaukee, Wisconsin. The image on the right shows our manufacturing facility. In this building, our application team, our engineers, our scientists, and our R&D is also housed. Our webinar today is broadcast live from this building. Over the last 10 years, Radom developed a core patent portfolio. There are actually over 29 patents and 3 applications worldwide. The patents revolve around high-frequency plasma generation. One of the first projects was to apply this technology to atomic spectroscopy. Additional patents have been approved in this vertical, but atomic spectroscopy presented itself well suited for this technology. Radom Corporation has further developed the IP to solve several key challenges that have been identified in the marketplace. So stay tuned to learn more. Before we can talk about MICAP-OES technology and how it reduces argon dependence, we first want to break down the commercialized ICP-OES systems available today. These are argon plasmas. Let's take the entire system and break it into 2 components. The first component would be the plasma source. The plasma source is the sample introduction and the torch assembly. In that torch assembly, the plasma is contained and generated, which we'll talk about in a minute. If this component is not robust and stable, there's no need for the second component, which is the spectrometer, which measures the concentration of elements in the sample. First, let's talk about the plasma source. So in the plasma source, we can see that argon is present from the time the sample is pumped into the nebulizer, carried through the torch, and injected into an argon plasma. Throughout this process, there are various flow rates of argon. If we did a summation, we would see it's about 14 to 20 liters a minute of argon, which is quite a bit. Argon is delivered to laboratories in a variety of ways depending on the sample throughput and the number of instruments installed in the laboratory. You can have cylinders. One cylinder will last approximately 8 hours. So as not to disrupt sample throughput, cylinders can be chained together on a manifold system and switched over automatically as one cylinder is depleted. Alternatively, Dewars can be purchased and installed in the laboratory. These contain liquid argon, which is pressurized, and then gas is delivered to the system. And these range anywhere from 160 liters to 234 liters of liquid argon. For very high throughput labs or where argon is also used within a facility, a mini bulk dewar can be sold. In this case, telemetry is used to notify the supplier when the argon needs to be replenished. But let's put this into perspective. We said that one cylinder lasts about 8 hours. But how much argon are we actually using? Well, if our sample analysis run takes about 2 minutes to run one sample, and we use the worst case, the highest flow rate of 20 liters a minute, we see that we're using 40 liters of argon per sample. Now, multiply that, say, by 100 samples a day, and now we have 4,000 liters of argon per sample. What about the second component, the spectrometer? Typical purge rates for a spectrometer are 0.3 liters a minute to 14 liters a minute. Now, these rates are averaged or compiled against all industry standard ICP-OES commercially available today. But in this case, vendors typically recommend purging with nitrogen. Why? To reduce argon dependence, reduce the running costs per test solution. And nitrogen is about 3 times less expensive than argon. I happen to have a quote with me from our local supplier. So of course these are quoted prices for this area in Pewaukee, Wisconsin. So if we look at liquid nitrogen at 230 liters in a dewar, the price is $130. If we look at the same argon dewar, it's $975. So you can see there's quite a bit of difference in sourcing of argon versus nitrogen. And the same is true for cylinders. So purging the optical bench with nitrogen instead of argon does reduce argon dependency. But how can we do more? Let's reimagine a commercialized system. This is the same graphic that we showed earlier, but instead of argon, we're replacing that with nitrogen. Assuming normalized flow rates, we know that we would still be 14 to 20 liters a minute. In addition, the same gas delivery options are available: cylinders, dewars, and a mini bulk source. However, nitrogen is different than argon. Nitrogen can be generated from the air with a nitrogen generator. So now not only have we reduced the dependence on argon, we've also reduced the dependence on a supplier to deliver argon. Again, we can optimize our laboratory workflow and have no disruption in our sample analyses. In this case, we haven't replaced anything. However, I'll show you in a minute, we do need to make some adaptations to the RF power supply in order to use nitrogen gas. How can we do this? Well, traditionally, we used a 3-ring copper coil connected to an RF generator. The RF generator has a set frequency of either 27 megahertz or 40 megahertz. In order to create a plasma that can operate robustly and reliably on nitrogen, we need to have a different RF generation system. Enter Radom Corporation and CeraWave technology. CeraWave is an advanced ceramic that can be formed into a ring and operates at very high frequencies. 2.45 gigahertz. The plasma formed is a result of this technology, and it's referred to as microwave inductively coupled atmospheric pressure plasma. Over the last few minutes, you've heard me use the term MICAP, MICAP-OES, MICAP-OES 1000. Now you know why it's called a MICAP. It's a microwave inductively coupled atmospheric pressure plasma. Let's dive a little bit deeper into the generation process. Here we see a conventional copper coil. When applied with an alternating potential, the charge distribution in a copper ring oscillates in the bulk material. This oscillation's causing electrical resistance and limits the current in the copper. If you exceed the limit, the copper will melt. What about zero wave? The zero wave, when applied with an alternating potential, the material creates a bulk polarization current resulting in 100 times higher efficiency current, producing 100-fold less heat in the oscillating coil. Therefore, no chiller is required, as it does in traditional RF systems today. Here we see the ring is positioned over a classical 20mm torch. In this case, in the radon MICAP-OES 1000, the torch injector is 1.5 millimeters. So it's a standard torch that does not need to be re-engineered. It efficiently, with no cooling, while carrying 100 amperes of RF current, sustains an atmospheric plasma purely via an inductive coupling into the plasma. What does this mean for the end user? We get an efficient overall plasma generating system that's substantially simplified. It reduces the weight of the plasma source by more than 50 pounds and the size of the power generation system. And what it really means to your final results is that you get a reliable, robust plasma and extended torch lifetimes, and the plasma is nitrogen. In this graphic, we can see zero wave and the torch situated within a magnetron. In this case, the torch and the system, the sample is injected into the base of the plasma, and just like in an inductively coupled argon plasma, the nitrogen plasma serves the same purpose. We see desolvation, vaporization, atomization, and ionization of the sample, all through the zero wave activation. Once we have light emitted, it's focused into the modular high resolution optical spectrometer. Let's take a look at a high level look at the MICAP-OES 1000 specifications. It can use industrial grade nitrogen at greater than 99.98%. The system will capture a shell spectrum from the wavelength range of 194 to 625. This is our current wavelength range. It's modular and portable. The sample tolerance is broad, anywhere from water to high dissolved solids to organic solvents. We use standard glassware, which we'll see in a moment, as our application team shows you how quick and easy it is to set up the MICAP-OES. There is an auto sampler that's integrated within our software. The input voltage with an optional inverter, we can use 120 volts with standard plugs. The plasma has a vertical torch with axial viewing, and the plasma tail is automatically removed with no operator intervention. The startup and warm-up time is about 20 minutes. And now, because of the portability, the modular design, and the lightweight configuration, remote sample analysis capability is now expanded. Here are the dimensions of MICAP, and you can see the total weight is about 62 pounds. The plasma source is approximately 42, and the spectrometer is the resultant. And here is our standard autosampler, which has 4 rack capacity and either 5 high volume standards, or 10 50 mil standard capacity rack. Here we see the MICAP-OES 1000 limit of detection. We certainly don't expect you to read this periodic table. It's a placeholder here so that you can contact Radon Corporation to acquire this information. The table to the right shows the resolution of our shell-based spectrometer, which is very similar to all industry standard shell-based systems. And finally, we can see our typical performance of stability. This is an 8-hour stability run. The standard was prepared in 2% nitric acid. The concentrations were normalized and plotted versus time, with accuracy of plus or minus 10% and precision of less than 3% over 8 hours. Hopefully, in this brief MICAP-OES 1000 overview, you can imagine how this instrument can fit into your current workflow, or how to re-optimize your sample analysis workflow. Because of its portable design, MICAP-OES 1000 can now be positioned where your sample is located instead of bringing your sample to your laboratory. It can complement your current technology, and it can help you make real-time analysis decisions in manufacturing, mining, and environmental monitoring. It can replace or complement handheld devices by providing the full spectrum or elemental fingerprints. And it also can solve potential manufacturing issues at the point of manufacture. Come check us out at SciEx next week in Covington, Kentucky. We will be presenting at the Glass Expansion Seminar at the Gulf Coast Conference, scheduled for October 12th. And on October 1st, MICAP configurations can be viewed at labex.com. Mark your calendars for November 30th for a Before You Buy webinar hosted by LabX and presented by Radon Corporation. And without further ado, let's meet our Radon application chemist team, who will provide a brief hardware demonstration as well as a general software overview and data processing. Remember, type all your questions into the chat, and we'll be happy to answer them at the end of our presentation in the order in which they were received.
I'm Eric Mon, the lead application chemist.
I'm Jake Biesterveld, application chemist.
And I'm Dylan Rabine, also an applications chemist.
Now Dylan's going to show us how to set it up.
This is the MICAP-OES 1000. The instrument is modular with the plasma source and the spectrometer. Before we get into the sample introduction assembly, or the SIA, I'd like to show you the Sarawave ring. This is installed in the instrument right here, and the torch will then be slotted up inside it like so, and the plasma will then sit right about here. Now we'll start the sample introduction assembly. Alright, to begin our sample introduction assembly, we'll start with our torch here and 2 of our gas lines assembled like so. You can take this lever here and pinch the lever to allow the torch entry. There are 2 pegs on the torch that will not allow you to place the torch too far into the instrument, and the orientation does not matter. The top gas line here will be going to the coolant, and the bottom gas line on the torch goes to the auxiliary gas. These 3 gases are all nitrogen. Next, we will be assembling our spray chamber. There is a clamp here that hooks on like so, and the spray chamber is responsible for filtering the droplets of spray from the nebulizer to get a finer solution up into the torch. Next, we have our nebulizer, and it just slides into the spray chamber. The nebulizer will use the nebulizer gas and combine that with our sample to create an aerosol, which is injected into the spray chamber. Finally, we have our pump tubing and our peristaltic pump. Now, depending on the speed of your pump and the size of your pump tubing, that will determine the amount of volume that goes into the nebulizer. So I would start with the farthest back line that you're going to assemble, which is our waistline. Clip both sides in. And then our sample line, which I'm putting in the front here. So those get clipped in on both sides and then clamped down on the top. Now this sample line will connect to the nebulizer like so, and the other end of the sample line, I'm going to be using this capillary tubing currently as a sipper for our rinse solution. For ease, you can use a small piece of sandpaper to grip the tube so that will prevent any bending, and that'll just use a little bit of force. And so we have that in our rinse. For our waste, we have our waste container that I'm going to be setting down below the instrument, and the tubing that will connect to the end of the pump tubing here. It's important to note that the pump will be turning one direction, so you need to have your sample line and waste line oriented opposite each other. So one end of the waste line will go to the waste container, and the other end of the waste line will go to the base of the spray chamber here. And now we have our sample introduction assembly set up. So we are almost ready to fire up the instrument. As you can see, we have the power turned on because it's lit up, but we have a red light here on the start-stop. So with a red light, that indicates that we're not ready to fire up the instrument. It could be a few things such as the exhaust or the gas is not being turned on. So Jake, you hit the exhaust. So we have our exhaust on and our 3 gases, which are nitrogen, argon, and compressed air. The nitrogen will be running all the coolant, auxiliary, and nebulizer functions, and the argon is only used for the ignition, so a small tank of argon can last you years. So now that everything's set up and we have a green light, we're going to ignite the plasma. And you'll notice that soon after the plasma ignition, the pump tubing will start to run, or the peristaltic pump will turn on, and we have our rinse, going through the sample introduction, and the aerosol is in the spray pan. So now I'm going to shut this down, and I will pass it off to Eric to give you a look at the software.
Yeah, I'll introduce you to the basics of the RIS, the Radom Intuitive Software. This software is built from the ground up for this instrument. So going to the main menu, I can also do that from the main menu. View sessions, view methods. The session menu, you can build a new one, edit an old one, import files from a different one, view the results, run it, resume it, generate a report, or delete it. Similarly for the methods, you can view methods, make a new one, edit an old one, archive it. On the instrument, we have the system status. Here we have the interlocks. In the overview, we have the camera, auto sampler status, plasma source, gas pressures, gas flow rates, a wavelength calibration for the spectrometer, temperatures of the interlocks, the ignition status, and the peristaltic pump speed. And the ones that are editable, you can enter a number and hit apply, and that will take effect. Now going back to the sessions, this is the sequence of events that you would run samples on. So just looking at open one up here. So you have the name, obviously, a method, the matrix, other fields that you can enter useful information. You can run it manually or with an auto sampler, and also choose how to end this session with the plasma off afterwards and the pump off or on afterwards. In the sequence of samples, you have the sample type as a standard or a sample, and you can enter in preparation parameters to get a correction factor. Going over to the methods, there are 5 tabs in the method. The general one just has basic information about the matrix, the name, any notes you care to put in. On the Elements tab, simply clicking on an element and a corresponding wavelength puts that wavelength down below. And these are all the chosen wavelengths for the method. Here you can enter whether it's an analyte or internal standard, the type of background correction, the background points, the type of peak area, and more integration parameters. Jake will go into the profiles when he goes into the data analysis section. Over here you have interferences. This is handy when you're picking wavelengths. They'll bring up a custom line library for the nitrogen plasma, where you can see if there's any potential interferences. Going to the Instrument and Sampling tab. Here you can change the gas parameters, the power of the magnetron, and the exposure time. This is also a time scan where you can change these parameters and look at the results of the output. Here you can do the sample uptake delay, stabilization time, 3 rinse times, and the number of exposures and the number of repeats. This time scan applies to both of these, so you can change all of these parameters and see the effect on the output. When this is displayed, you can do a normalized or the raw data. Going over the Standards tab, you can add standards, remove standards, put in the concentrations through origin, if they're weighted or not, the weight of them, the fitting method, your minimum correlation coefficient, and your standard error for the standards. The final tab is the QC tab. Clicking on any one of these puts this into the choice in the session. So back to the sessions, we had the sample types, the standard, sample, and if one of these are chosen, this will be a choice in there too. And that's a quick rundown of the software. And here's Jake to go through some data analysis.
Alright, so we're going to jump right into a session that has already been ran. So as you can see, all fields are grayed out, indicating that each line has already been ran on the instrument. We're going to click View, and here is the data analysis page. You can slide this middle bar to the left and right to display different portions of your data. So we're going to shrink that a little bit so we can see everything in view here. From left to right up on the top, we have icons that allow you to report your data, expand all your rows so that you can see all of your replicates. You can also click the icon next to that to collapse all of those rows. Similarly, you can do the columns in the same way, and this will show all relative data that you have selected for your view. So by default, it will show you your final concentration, your final RSD, your intensity values, your intensity RSDs, your initial concentration, and your internal standard recovery if you have an internal standard attached to your method. If you right-click, you are able to add and remove data that you wish to see. You're also able to sort alphabetically by chemical symbol or numerically by wavelength. If you'd like to show more of your preparation parameters, you can select these and they will appear on the left-hand side as such, so you can show measurement time, your initial weights, final volumes, and your dilution factors, which will all automatically calculate into an overall correction factor. So we will shrink that back down, and you are able to collapse all of your columns similarly to the way that you can collapse all of your rows for easier viewing. We have an icon here that's labeled ISR. This will either, you can apply your internal standard correction or not apply your internal standard correction. Anytime any data is changed, you must click Recalculate to show the applied results to whatever changes you made. So we'll keep internal standard correction on. This icon will allow you to go back into your method and add a line that was not previously analyzed. So if, for instance, your two iron lines did not work for you, to see a third, it will populate on the bottom just as if you were editing your method originally. You click the Standards tab and make sure that you fill the correct data into here. So if you highlight the field above and the field below that you wish to fill, you're able to right-click and fill numerical columns, and all data that has a numerical value will fill automatically. Click Save here. It will ask you if you'd like to save your change into a local copy of the method, a global copy of the method, or both at the same time. Right now we're just going to save it to the local copy of the method, which will not affect the overall method applied to future sessions. It will only affect the current session that you're viewing. After a brief recalculation period, your new line will appear amongst the old lines. But as you can see, the data is not going to be integrated properly here. So we're going to click our Profiles button. Here you're able to select which standards you would like to view. So we're going to click Select All and hit OK. Now here we have the Profiles window. If you'd like to see all of your points at the same time, you can hit Select All. If you'd like to not view all of your data and only do one at a time, you're able to select these checkboxes and only view the relevant data that you wish to see. I'm going to look at all of them right now, and we're going to go over to our line that we just added. So here we see that it defaults to a 2-point integration system, and this integration is not correct for these peaks. As you can see, the center of your peak is not centered within your integration points. So to get a better view, we're going to select our highest standard here, and this will highlight between the two integration points the area of your peak. We'd like to move these out so that we get a more accurate representation of our peak. And so now you can see our entire peak is selected, and there are no interference to the left or right, so we are okay with a 2-point integration. If you'd like to see, or if you do have spectral interferences and you'd like to have a more complicated approach to your integration, holding Shift and dragging one of your lines will separate them into different integration points in which you can move wherever you'd like to get a more accurate integration. You can do this up to 2 times per line for up to 6 total integration points. And so here's an example of a 4-point integration. And if you'd like to expand your shoulder points for an even more accurate integration, you are able to do so. If the changes you've made are not sufficient to what you'd like to see, you can always click your merge lines and it will go back to a 2-point integration system that just allows you to start over from scratch essentially. If you don't want to shift click your lines, you can also click reset and that will give you a 6-point integration to which you can start moving your points back to where you'd like them to be. So we're going to keep it at a 2-point integration right now and expand out in our entire peak. On this bottom portion of the menu, you have options to look at the averages of your samples and blank, or all points on top of each other. We'll keep it at the average for now. Here you're able to select which wavelength and which element you'd like to be viewing at one time. The span section will allow you to increase or decrease the amount of data that you're looking at. So if we'd like to see a wider portion of the graph, you can select a different numerical value in nanometers and hit enter, and you will see a larger portion of the graph. Similarly, you can also click default, and that will give you back the default 0.1 nanometer range. Double clicking on anywhere in this field will snap the picture back to incorporate all data points. Here we have numerical values in picometers for your integration points. So as stated previously, we are using a 2-point integration system where the left shoulder point is going to be equal to your center point, and the right center point is going to be equal to your right shoulder. If you separate these out, these values will change. As seen here, we now have a right shoulder point of 17 picometers away from center, and your center point is going to be equal to your first right shoulder point. I'm going to merge those lines again. Here you're able to select a different correction factor for your peak area. So right now we're using linear. You can also use exponential 1 or 2, and Gaussian 1 or 2, or none. Here is the area data shown here numerically. So you have your blank, the correction factor applied, and the corrected sample value, along with the standard deviations, signal to noise ratio, and the RSD of the specific point you're looking at. We're going to click save here, and same as before, we're going to save it to the local copy of our method. And after another brief recalculation period, you will see that iron 238's values will change according to our integration. So we now have approximately 95% recovery on a 100 ppm sample for our drinking water. Once you have done the integration parameters for all of your elements and all of your wavelengths, you are able to click the report button, and you will see a list of options to put into your report. Clicking full report will include everything on this list. If you'd like only portions of this list, you click concise, which is the default, and you can include any relevant information, including final RSD, intensity RSD, initial concentration, internal standard recovery values, your calibration curve equation, your R squared and LOD values, along with your preparation parameters, overall correction factor, sample measurement time, and auto sampler location if an auto sampler was used for your run. You are able to sort the report by your chemical symbol alphabetically or numerically by wavelengths, and you are able to select the report format, which currently is a CSV. You can add comments, and you can also choose the file path location for where you would like your report to populate. So here we're just going to go ahead and put it on the desktop and name it whatever you'd like. We'll name it webinar and we'll save. Now that we have the proper file location set, we can click OK, and it will ask if you'd like to open the folder containing the report that you just generated. You can see now that the report has been generated.
Well, that ends our current presentation. We hope that you found the information useful. We hope that we've sufficiently described MICAP-OES 1000.